under the, not if it's part of the radicand. If it's part of the radicand, it just gets released. And minus 9. Now, can I go further than that? No. These are unlike terms, so I'm not going to get down to a single number like I did here, but it's fine. The point is, no more radicals. Okay? So, two important rules here. Well, let me introduce 11.5. Okay. So, 11.5, and if you're reading ahead in the text, 11.5, we're only doing a portion of it. 11.5 is basically two sections, one called rationalizing a denominator and one called rationalizing a numerator. Cannot for the life of me understand why they bothered to do rationalizing a numerator, because that's just not something we do. Okay? So we're only doing rationalizing a denominator. Rationalizing a numerator is just silly. So this is a skill called rationalize a denominator. Now, all you're doing right now is applying your radical rules, your radical skills, in order to do this thing that I'm about to show you how to do. And you might be like, okay, so why? Okay. Well, no worries. You're not actually going to use it in context right now. You're just going to learn the skill. It helps you learn the properties of radicals. But later on, towards the end of 310, a little bit towards the end of this class, especially in college algebra, rationalizing the denominator is about basically putting something in the proper form before you walk away. Okay? Rationalizing a denominator just means this. It means that you have no radicals in a denominator. So if you have a quotient, and it has a radical in a denominator, that is not good form. And you want to get rid of the radical in the denominator. It's kind of like putting it in lowest terms, so to speak. You know, you're cleaning it up. You're putting it in the proper form before you walk away. And generally the proper form says never walk away from an answer if it still has a radical in the denominator. Okay. Now, aside from me just saying rationalize this denominator, you'll see the problem. You'll get rid of the radical in the denominator and you're good. Be like, okay, so why? Well, later on, it's a technique for cleaning up an answer in other contexts. Okay. So for now, you're just going to do it, and it will come up again later. But I will say that a lot of, even mathematicians disagree on whether this is really a thing. There's argument about whether this is really an important thing to do or not. So we learn the skill because some people still say yes. And it's a pretty basic skill. Some people still say yes, some say no, but don't overstress about it. But rationalizing a numerator, not a thing, so ignore that in the book. All we're doing here is we're killing radicals. So you're going to kill the radical that's in the denominator, because we don't want it there. Before we walk away, if there's any radical in the denominator, we have to get rid of it. But we have to do it in a fair way. Okay? So we have to kill radicals according to our fair mathematical rules. Okay? And we're going to use two of our properties to make that happen. If our denominator is just a single radical, okay, then we use the property that if we multiply a radical times itself, okay, what happens? It becomes A. Oh, no more radical. Okay. So if you have a square root of A in a denominator, and you want to get rid of that radical, multiply it times itself, and it becomes A, no radical, and as long as you do the exact same thing to the numerator, then it's a fair and legal move. Okay. And if instead your denominator is actually a binomial, okay, I'll say the denominator is a binomial like square root of A, it could be plus another radical or maybe just a number. Okay. So if your radical has a binomial that has a plus or a minus, how can we get rid of radicals? Okay. We want to square it, right? But not if we square the whole thing. Remember, a binomial squared has a middle term that still has a radical. Conjugate. Huh? Conjugate, right. We multiply it times something, not times itself, because then you'll still have a middle term that has a radical. Defeats our purpose. But if we multiply it by its conjugate, conjugates kill radicals. Now, depending on whether you have a variable or not, you might still have a variable, or you might just get down to a single number, but the radicals will be gone. Okay? So that multiplies into A minus, and then if this is just a number, it'd be A minus, squaring that number, whatever it is. Okay? But no more radicals. Okay? Okay. So, first we'll look at the ones where we just have a single radical in the denominator. That's mostly what we're focusing on. This one can get really complicated and ugly and chaotic looking. I kept it really simple on the homework and the examples I'm about to give you. We're not going to go overboard with it. But you do want to understand the general property and how to clean that up. So 3 over square root of 5. There's a quotient. You're told to rationalize the denominator, meaning if there's a radical in the denominator, we need to get rid of it. How will we get rid of square root of 5? Right. Now, as long as we are fair to the top and do the exact same thing, all we're doing is multiplying by 1. Anything over itself equals 1, and multiplying by 1 is the identity. Doesn't change anything, doesn't change the value. Fair move. So what is our new numerator? Yeah. And our new denominator? 5. That's it. No more radical in the denominator. Now some variations on this involve, if you can do any cleanup work first, do so. For example, here we have a quotient 1/7 and the entire thing is under the radical sign. And you're told to rationalize that denominator. But can you touch that denominator yet? No, it's kind of mixed up in here with the rest of things. I need to break things up first so I can focus on the denominator. I can't really touch just that denominator yet because the whole thing's under one house. So what's the first thing I should do?
Separate them.
Yeah. By the quotient rule of radicals, I can break it up into 2 houses. Now I can touch that denominator, but before I do so, any cleanup work or simplifying I should take care of first. Can I do anything with the numerator?
Yes.
Yeah, square root of 1 is?
Square root of 7. Oh, yeah, square root of 1.
It's just 1, yeah, over square root of 7. Okay. So now I can rationalize the denominator by multiplying it by itself. Be fair to the top. My new numerator is?
Square root of 7 over 7.
Over plain old 7. Negative 7 square root of 3 over square root of 11. Actually, let me do this. Make this over 2 square root of 11. So negative 7 square root of 3 over 2 square root of 11. Now we're already broken up into 2 houses. Okay, so that's fine. We can access the numerator and denominator separately. Is there anything to simplify with the square root of 3 or square root of 11? No. So we're ready to just go ahead and rationalize. So what should I multiply the bottom by? What about that 2? Yeah. We don't care about the 2. It wouldn't be wrong to multiply by times 2 times square root of 11 as long as I multiply the top by 2 times square root of 11. That would be mathematically fair because I was fair to the top and the bottom, but why involve the 2? Why make bigger numbers if I don't have to? Okay? My goal is to kill that radical, so my only goal is to get rid of that radical, so I get rid of that radical by multiplying by itself. I don't have to also multiply by 2 again because I'm not trying to kill that 2. The 2 is fine. Okay? So don't make more work for yourself. Just multiply by the radical. So on top, same thing. So across the top, now this is negative. Okay. Now, my new numerator is
7
square root of 33. Right. 2 different radicands. We can multiply them under one house, but they're still a house. 7 square root of 33. And on the bottom, right, 2, which is already there, times square root of 11 times square root of 11. So it's 2 times 11. Anything I can simplify with 33? 1 times 33, 3 times 11. Yeah, no, it's not a perfect square, no perfect square factors. So it's 7, negative 7 square root of 33. I would simplify if I could, but there's nothing to simplify, over 22. Now, can I simplify that 33 and 22? No. One's radical, one's not. That is not actually 33. Square root of 33 is a totally different value. Don't be deceived by that. I would, if I could reduce 7 over 22, then I would. I can't, but I would see if I could. And that would be legal because they're both free-floating numbers. Okay. So one last one here, and then we'll do one with a couple with the binomial on the bottom, and then we'll just introduce, hopefully we'll have time to introduce a couple of equations so you can get started on that. So we got 6 over square root of 18x. Okay. Told to rationalize the denominator. But before you do so, clean it up as much as possible. You could go ahead and multiply this times the square root of 18x on top and bottom, but it just makes it a lot messier, bigger numbers. It's generally easier to clean things up first, simplify things first. Then you're multiplying, you're rationalizing with the smallest possible radical. Now, 18 is not a perfect square. Does it contain a perfect square factor? Mm-hmm. And x, perfect square or not? No. So there's going to be some leftover bits. 9 times 2, 2 is the leftover bit. 9 is the perfect square, 2 is the leftover bit, and x is also a leftover bit. So 18x is the same thing as 9 times 2x. But by the product rule, I can root and release. Square root of 18x is the same thing as 9 times the square root of 2x. Rooted and released the 9, 2x was trapped behind. Now, can I go ahead and multiply the top and bottom by square root of 2x? I could go ahead and do that, right? Would I multiply times 3 also? Not necessary. If it's not a radical, it is there. But to rationalize, I just have to multiply it by the radical to kill the radical. What's something I could do to clean up a little bit more, though, even before I do that? Yeah, and I don't have to do it right now. I could do it at the end, but it's a good idea. Clean things up as much as possible. 6 over 3 becomes 2 over 1. Okay. That's legal because they're both outside. I wouldn't do 6 and 2. 6 and 3 is fine, giving me with 2 on top and a square root of 2x on the bottom. So that's all just cleanup work. Simplifying a radical that had a partial perfect square, okay. Reducing to lowest terms. So I'm going to take that 2 over square root of 2x and now rationalize it. Fair and legal move, basically multiplying it times 1. My new numerator. My new denominator. Am I done? Yeah. This one, the outside or inside? Outside, right. That one's locked up, can't interact, but those two on the outside, 2 over 2 is 1. Basically, they cancel out. So you got square root of 2x on top and just a plain old x on the bottom. Not too bad, right? Like I said, you may not see, like, why do I need to do this now? Right now, it's just about being really comfortable with those skills, how you accomplish it. That's something that will come up, the further you go in math will come up later as something you require to do. You wouldn't leave an answer like that. You would have to rationalize the denominator in order to finish cleaning up your answer. But understanding that the properties of the radicals to do so is that multiplying a radical times itself kills the radical.
So, question. If we didn't have to simplify first, and we went ahead and just multiply it by the 18x, it's still...
Yeah. So 6 over square root of 18x times square root of 18x times square root of 18x. This one's not going to be too bad. Sometimes when you do this without simplifying, it gets you some really big numbers. So in general, across the board, simplify first. Okay? But if you do this, you still get to 6 times square root of 18x over 18x. Now you can go ahead and simplify that sum and get square root of 18x over 3x. Doing 6 over 18 becomes 1 over 3. You still have to simplify 18x though. So whether you do it at the beginning or do it at the end, I always find it generally cleaner to do it at the beginning. It's easier to add bigger numbers and get mixed up with it at the end. Mathematically, you can approach it either way. This is just my strong recommendation. Because at this point, you would simplify that to 3 times square root of 2x over 3x. Then those cancel out. And you still end up in the same place, square root of 2x over x. Yeah. Mathematically, you'll get there, whether you clean up first or clean up at the end. So ultimately, it's your preference. Try both when you're doing your homework. See what works for you. This is my strong recommendation, but this is mathematically correct as well. That answer your question? Is that?
Yeah.
Okay. So that's when every example we've had so far has been a single radical in the denominator. Yeah, it might have a coefficient or whatever, but it's just a single radical, no pluses or minuses. Okay? So how about this? We've got 2. Here's a quotient, 2, but it's over, instead of a single radical, it's over 4 plus square root of 5. Now this is a binomial with a radical in it. If you got a plus or a minus, you can't just multiply this times square root of 5. Because then you would be distributing square root of 5 times these two things, and you would still have a radical. That wouldn't accomplish anything. So this is a binomial, so lock it up as a matter of course. And what should we multiply it by if we want to kill that radical?
By itself?
Well, by itself it would be 4 plus square root of 5. And that would be a binomial squared, and we'd have that middle term with a radical. So conjugate is what we want. Yeah. Times itself will give you a middle term with a radical. Binomial squared have middle terms with radicals. Conjugates, however, have no middle term, so it kills the radical. So if this is plus, then we use minus. If this were minus, we'd use plus. Be really fair. A common careless mistake is actually putting the wrong one on top. Whatever we do here, we do the exact same thing. Okay? So we're multiplying by the minus version of the conjugate, so same thing on top. Now, you do not have to distribute and multiply this out. Just write it like this. 2 times 4 minus square root of 5. Okay? You don't want to distribute now because you may be able to do some more canceling. You want to leave it in factored form so you can cancel if necessary. Now there's some big, ugly, complicated ones where the numerator isn't just a plain number, but it's another binomial itself, and then you have to FOIL, and it's big and ugly and messy. I didn't give you any of those on homework. I want you to get this basic concept understanding of conjugates and killing radicals. But they're going to be, at most, like this. So leave that factored. And on the bottom, conjugates make a difference of squares. First term squared minus the second term squared, in that order. We're done with the numerator. We're just dragging it along, and then this is 16 minus 5. 4 is just a number. It gets squared, and this is a radical squared. The answer is the radicand. So 2 times 4 minus square root of 5 over 11. Now, because we left the numerator factored, we can look at that 2 over 11 and, if possible, reduce. Okay. In this case, no. But sometimes your numerator will be negative, depending on the order of your binomial. This might have been, if this were in the other order, it'd be 5 minus 16, it'd be negative 11. If that were the case, for the final answer, just pull the negative out front. Don't leave it on the bottom. Because if there's a negative on bottom, you could put it on top or you could put it out front. That means the whole thing is negative, so you just pull it out front. Negative 12 over square root of 6 minus 3. Oh, yeah, that's it. That's all. Yeah. Yeah, don't multiply out the numerator. You just check to see if you can cancel. Once you simplify your difference of squares, the conjugates, difference of squares, simplify. Just make sure you can't cancel any, reduce anything, and you're good.
We don't distribute.
No. You could, it's mathematically fine, but if you distribute first, then you won't know if you can reduce, and that would be wrong. You'd have to refactor to reduce. In the end, why make more work for yourself? Just leave it factored. No. It's not, at the end, if you did multiply it out, it's not wrong, but not necessary. Now remember, this one was plus, so you multiply by the minus. This one's minus, you're going to multiply by the plus. Lock it up. Make sure you do the same one on top. Don't mix up the signs on that. Let's just it's distribution, but don't distribute. Just leave it in factored form. Now, is this final answer going to be negative or positive? Yeah. Because we had a negative on the bottom, but also a negative already on top, so it cancels out to positive. If one of them were negative and one positive, we would just pull the negative out front. But they're both negative, so they just cancel out. And you can also reduce the 12 over 3. Positive 4 over positive 1. And that one's flat. It doesn't have a denominator anymore because it canceled out. Okay with that? Okay. So that's 11.5. Okay. Rationalizing denominators, just those. A few problems with some single radicals and some that are binomials. All right. So let me introduce 11.6 so you can get as far as possible with the equations. Okay? Because we'll do some more complicated equations on Tuesday, but I at least want you to get a good start, understand the rules for solving radical equations. Okay. So this is 11.6. Solving radical equations. Now from the last unit, Unit 2, which is Chapter 10, we solved rational equations. Rational equations were, like fractions, but with polynomials. Okay? So to solve a rational equation, an equation that had at least one rational expression, it was necessary for us to first kill the rational. We couldn't solve a rational equation. That was the whole point. So our first step was to kill the rationals, to kill the denominators. So to solve a rational equation, we multiplied every term by the LCD over 1. That killed the denominators and flattened it out. Because we couldn't solve a rational, so we flattened it out, and then we had either a linear or a polynomial, a linear or a quadratic. So we'd either solve the linear for x and get one solution, or solve the quadratic by putting it in standard form and factoring and getting two solutions. Okay? And were all of our solutions good? Or did we sometimes have to throw one out? Remember at the beginning with the rationals, we'd look for our restrictions. Yeah, anything that would make any denominator undefined. And we want to do that at the beginning. We did that when we found our LCD, so we used the LCD over 1 to kill the denominators, solve the resulting linear or quadratic, and then made sure that those solutions did not violate the restrictions, because if they did, we had to throw them out. Okay? So we couldn't solve a rational equation. We had to do something to turn it into a linear or quadratic, solved by either the general strategy or by factoring. And we got all the possible answers we might have, but some might be bad and we had to throw them out. It's exactly what we're doing here. solving radical equations, we can't solve radical equations. Our first step is to turn it into a linear or quadratic polynomial. And if it's a linear, we'll solve for x, and if it's quadratic, we'll put it in standard form, factor, and get 2 solutions. But, just like with rationals, we're going to get all the possible solutions to those polynomials. That doesn't mean they're good solutions to the original radical. So we have to check our work. Now with the rationals last unit, we could know right away if something was bad because we could see if something made it undefined. We'd find our restriction, so we'd know if it was bad. That's not the case here. Here we have to do the work, and then we have to check our work. Okay? It's not going to be as obvious as before where you can find a restriction in advance. Just whenever you get your answer, before, check your answer if you have time because it's a good idea. Here you have to check your answer because you may have to throw out a solution. Even if you did all the work right, you may still have to throw out a solution. So you have to check your work here. Okay, so to do this, to change a radical equation into a polynomial equation, either linear or quadratic, we use what's called the power rule. And the power rule just says this: we are going to raise, it is a legal move to raise both sides. And let me emphasize that, sides, not individual terms, not leaving anything out. You put parentheses around both sides, parentheses around the left-hand side, parentheses around the right-hand side, and you power them both up. Okay? So raise both sides to the same power. Now obviously you're going to use the power that matches your index. If you have a radical equation that includes a square root, you square both sides. If you have a radical equation that involves a cube root, you cube both sides, because that power cancels out the index and kills the radical. That's how we kill the radical and turn it into a polynomial. Okay? By canceling out its index with a power. And as long as we're fair to the other side of the equation, it's fair, and we're left with a linear or quadratic that we can solve. Okay? Now always, remember, this is the solutions. When you do this, the power rule is legal, but it may result in what's called extraneous solutions. Extraneous solutions aren't bad. It doesn't mean you did anything wrong. It just means that there are solutions that did work for the polynomial you just created, but they don't work for your original equation. Okay? So it may result in extraneous solutions. You need to check your work, and anything that is extraneous, it's not good for the original equation, you throw out. Okay? So it's a legal move, but it may give you more solutions than are actually true for the original equation. But all of the solutions will be among those solutions. It's not going to leave any solutions out. You might have to throw some out, but it's not going to leave any out. You'll get all the possible solutions, what's called proposed solutions. Okay. So your basic steps are this. 1, you must isolate. If you remember when we did the absolute value equations at the beginning, a long, long time ago, in order to do what we're about to do, you have to isolate. We had to isolate the AV on one side, same with the radicals. We must isolate the radical first. Okay? So get it all alone on one side. If it has anything added or subtracted to it, not under the radical but outside the radical, move it over to the other side. If it has a coefficient in front of it, divide both sides, divide it away. Okay? So it's all alone on the left, generally on the left. 2, power up both sides. And again, I'll emphasize sides. Put parentheses around both sides and power them up by whatever the index is. 3, you solve the resulting linear or quadratic. And 4, can't skip this step even if you're running low on time. It's important.